and probably I'll talk something small about it. So I've been looking at DEA, and I was wondering how I can be able to do some farm level crop analytics. How can I use it to do crop monitoring, to help smallholder farmers, crop identification or crop classification and all that. So that inspired me to look at DEA, and I was amazed at how DEA has stored its data in an X-array data set in a time series manner, which would enable me do the crop analytics and the crop classification. I've not yet done crop prediction, crop yield prediction, but I'm still it is on my roadmap. So it's still work in progress. I've not done so much in this script, but after this meeting, I hope we will discuss something small about it and see if we can be able to collaborate on the same to be able to make the script better and encompass other variables that I have not included in this crop classification task. So I've imported the using the sandbox. I've imported the necessary packages, the one from the data cube and also others like GeoPandas and Rasterio. And after that, I've identified the area of interest. Okay, when we're talking about crop classification, in most cases, we always need some agricultural level data sets, which I can say we do not have much at the moment. So whatever I've used, it is just I can say from expert knowledge, because I come from this place and I kind of know some of the places that grew maize, because I was just trying to do some crop classification on maize. So I just created two masks, maize and others, that is forest and other things. I did put it in the other class. So using some expert knowledge, I tried to see areas where I had maize the previous year. This is for 2020. So I created polygons for the same. I did some digitization and I uploaded or I imported the data into this script. So the time range is between 2020 April and 2020 December, because this is the crop calendar of growing of maize in Kenya, particularly in Rift Valley, North Rift, yeah. So this is the crop calendar. It's because of the climatic conditions. It takes quite some time for the crop to grow. So I did some buffer, and this is the area of interest that I was trying to look. As you can see, there is a very big forest here, and there are some places which you can see look like the farms. Okay, using the query, we imported the analysis ready data, and you can see that we had around how many time steps? Around 48 time steps. That is from April to December 2020. We had around 48 time steps. Of course, I couldn't use all of them. Then after that, I read in the JSON file that had the data, had the labels, the polygons that had the labels for maize and the other classes. So I imported it in. Then after that, I chose some specific time steps. I did it manually because I wanted some time steps which did not have gaps because of course of clouds. So I tried to look for some time steps which did not have much cloud cover. Then I iterated over, I iterated over the time steps that I had chosen. So what I'm doing in this cell block is I'm trying to use Rio X-Array package. Of course, all these are built over the GDAL package, which is used to manipulate raster data. So I'm trying to use this package to clip the farm polygons, so that I can be able to get the values. I can be able to get the bands, the red, blue, and green, and that I'll use as features in my machine learning model. So as you can see here, I've clipped using Rio X-Array. Then I've stacked together whatever I've clipped. Then using, of course, using NumPy, and its methods. Hello.
Yeah, Steve, we can hear you. Please continue.
Okay. Yeah. So using NumPy with the methods that NumPy has, NumPy is a very, can say it's a very robust package, Python package. Using its methods, like for example, trying to find in the NumPy arrays, trying to find those pixels that are mass pixels that do not have data, and also using packages like Agware. I created a features array. As you can see here, first I started with X row and Y row. So I appended all the features that I need in my crop classification task. I appended them into this array that I've created. Then after that, sorry for these. Then after that, I turn the list, the X row and Y row lists into a NumPy array. Then of course I do the splitting, the training and the test sets. Then I do the creating the class weights to take care of the class imbalance in the data sets that I have presented. Then I use the random classifier. It's an ensemble. I use the random forest classifier to do the to create the model. Yeah. I don't know. Should I run the should I run the notebook, or I finish first explaining?
Oh, I think after you finish explaining, you can run it.
Okay.
Yeah, depending on the time it takes to run.
It takes a very little time to run.
Okay, yeah. So okay.
To see if my classifier did some justice. Then after that, okay. After creating now the model, we now want to, you see this window that I created here. We now want to, I've already created the model. Now we want to classify all the pixels here and see which are the other classes. So so what I did here, I used the GDAL write function. Okay, here I'm using Rasterio. Of course, Rasterio is built over GDAL. So I use Rasterio, and these are I don't know how to call them, but this is what is needed for me to write. This is what is needed for me to write back that TIFF file. So in this cell here, what I'm trying to do is I'm trying to take the data in that whole window, the red, green, blue, and near infrared data. I'm trying to take all that data and flatten that data in a way that I can be able to use it in the machine learning, in the crop model that crop classification model that I already created. As you can see here, after I put it in a format that can now be used to predict, I do the prediction. Now, after doing the prediction, now I have to resize it to the original image dimensions so that I can write it back now as a TIFF file. And at the end of the day, we will get a TIFF file, a classified TIFF file that will represent this window that I indicated in the first place here. Okay, so I think I'll run the whole. I'll run the whole notebook. Pardon me, I'm not very good in explaining. So if you feel the problem, if you feel like there is something that you need to know or something that you didn't understand, you can as well just ask me.
Okay, Steve, I think this is a very great presentation and a very great work done. Bravo on that. So right now, Stephen is running the work fast to see the results, but whilst the process is running, if there's any question you would like to ask Stephen in relation to the work, and also if there's any comments that can also improve the work, you can kindly ask during this time. So you can use the raise hand, yeah, you can ask the question, or maybe use the raise hands button for us to call you out, or you can speak directly.
Yeah, as probably somebody is planning or preparing to ask a question, in this machine learning task, I only used 4 features, and these features are the bands, the 4 bands only: the red, green, the blue, and the near infrared bands. I'm continuing. I'm in the process of making this script better, because I know that we can add other features like vegetation proxies, NDVI, red edge index, and all those, which can be able to help us create a good classification model. Plus, also, I've not done some error handling stuff. I've not created more functions to make the code more readable and all that, but I'm still in the process of doing that. So if anybody would be willing to collaborate in this, so that we can be able to create a good crop classification model, then they're welcome.
Okay. So yeah, Brian.
I had a question. So, sorry I was a bit late. I was having trouble with my camera, but the goal, if I took away correctly from the presentation, and I know I came in late, was classifying crops in a specific area, right? And the overall process was you were drawing shapes around certain fields to get their kind of signature, and then once you knew what was in each one of these fields, you created a random forest to then try to create a way to classify the different fields as, like, you could come back and reclassify new fields, right, as either corn or not corn or something like that, right?
Yes.
Okay. How many classes? I guess I missed the first part of it, but how many classes were you you said you had 4 different bands that you're using. How many classes were you trying to
It was just trying, the 2 classes were just maize and others. So I clamped
Okay.
I clamped all the other pixels as others.
Okay.
Yes.
Interesting. And are you getting good results yet, or are you still? Is it what are the do you?
Yes, I'm getting results, but they're not as good as I'd wanted them to be. So it still has the salt and pepper effect. Yeah.
Yes.
The file is called signore1.tif. You can get here. It is. Let me download it, and you can visualize it in QGIS.
So to spare you some time, this reminds me of the in the frequently used code, there is an image segmentation example notebook. Have you had a chance to take a look at that notebook before?
No, I've not seen that image segmentation, but I think that would really help.
So just from a tedium, like creating the fields can be kind of tedious, and that notebook kind of shows how to segment the image and actually group pixels together into actual segments. And that may actually, one, get rid of the salt and pepper effect,
yes.
but two, also kind of take away some of the tediousness of like having to maybe group the fields together. I'm interested. It would be interesting to see how you maybe could apply that in this case. And what's kind of nice in that example is they are actually looking at fields. Like that's actually one of the applications for this.
Okay. I think now I'll need to have a look at that segmentation, because as you can see from this image here,
right,
this is the classified image.
Right. A little disappointing.
A little disappointing, but as you can see, the black ones are the ones that are probably being identified as maize fields.
Right. Okay.
You can see that forest here. It has at least, you can see there is some. You can't see maize in there, so there is some hope. From this, I can say that there is some hope, but there is a lot of salt and pepper.
Yes.
And the way you've said it, the best approach would be to an object-based classification. So image segmentation would be really good. Then I can be able to now do the classification and all that from the segmented parts of the image. So
right.
Thanks so much, Brian. I'll take into consideration the use of image segmentation to improve.
And then another quick comment, which might also be helpful. Your ultimate goal is a geotiff, correct?
Yes.
Okay. In the there is actually a pre-written script to export a geotiff in the script section, and it's array to geotiff. Now, I saw you were using NumPy arrays, so it might not be applicable here because I think it's designed to take in an X array. But the X array would allow you to keep the data type that you get out of the data cube. That might kind of simplify, because it looks like you were using raster IO and you were having to manually provide a lot of the details.
Yes.
For
okay, let me take note of that.
Which is fine. I mean, it works. It obviously works, and but if you want to save some typing, you know.
Okay. I'll take into consideration on that.
Very interesting presentation. Nice job. You've obviously done a lot of work.
Thank you.
Okay. Thank you, Brian, for the comments, and also thank you, Steve, very much for the presentation. Steve, I also wanted to also add this to it. If you can go back to your sandbox and go to the real world example. Real world examples, yes. One of the folders, yes. There is another folder called Scalable Machine Learning. That's the folder, yeah.
Which
Yeah.
one? This one, machine learning with
The
object.
scalable, the scalable is a folder. The
Oh, it's
scalable machine learning.
okay.
Yes. So this
Oh.
notebook also takes you how to do classification using machine learning, whereby you provide your data to it, and it is grouped into 6 different types. So you can also take a look at this notebook, which I think it will be much more helpful to you in your crop classification. Yeah,
Very
to
true.
do the same thing. Yes.
Thank you.
So,
I never know that this was there. Actually,
yes.
looking at machine learning, I just saw this one. I just saw the other one. Oh, sorry.
Oh, okay. So you can go through the So you can go through this and let's see the results that will also come out of it. And if you have any challenges, reach out to us. Then we can actually go through together and resolve it.
Okay. Thank you.
Okay.
Then again. Okay.
Yeah, Steve.
Something to Brian.
Yes.
Okay. Also did something else. You see, we have a notebook here. It's called crop health. I think it's crop health. Is it crop health? I'm not very sure, but a machine, a notebook where you can go and it's crop phenology, vegetation phenology.
Yes.
But I'm not very sure, where you draw the boundaries of the farm. You draw the boundaries of the farm, then it gives you such kind of a time series plot to show you how your crops are. Okay, I also did something smaller on the same, and what inspired me to do this is the fact that in that notebook, there is no place where you can be able to upload your data and let the notebook do what? Create those profiles for you. So I decided to do something small of the sort, but I know, of course, probably there is a way in which you can do that.
Right. So I believe it's the crop health notebook you're referring to, correct? And what's kind of, I guess, frustrating from is that a lot of the functionality of that notebook is hidden in the notebook crop health script that's in the scripts folder. So I'm not surprised that you hadn't seen the scalable machine learning. There are a lot of notebooks and a lot of folders to go through, and so but in this crop health, so if you see right there, it's saying when we're at the very top cell, the first cell there, it's importing these two functions from the notebook. So first it says append to the path this directory, up one directory into the scripts folder. And then it's saying from the notebook app _ crop health file, import these two different functions. And those two different functions, that one right there. There's a lot going on here. And they are it's nice because it's kind of, if you wanted to show somebody sort of like what the data cube could do with like kind of like hiding some of the complex code in the background, that's why these two notebooks kind of are a good example of that. But if you wanted to make something to export and you wanted to access some of the data that's being created from one of the bounding boxes you draw, and you wanted to, for instance, have every bounding box you draw like exported to a file, you could add some Python code in this script to do that. And it would be the same type of Python code that you would put in a regular notebook. And so so there's some draw controls that's not so important. Keep scrolling. Let's see. It might take some doing. So okay, so you just passed. So here it's actually when we see this xr.plot, right? It's actually taking an X array and then plotting it there, right? And to generate that stuff. So that means you could access, so the XR variable, you could probably take that XR variable and then have it write to a file if you wanted to insert some of your own code there. The only thing you need to do to make this work is you put your code here, you save it, and then you just need to restart the kernel for it to reload this file. And it should do what you want it to do. Now, you may crash it, you may have some bugs, the first time around, but that's very normal.
Yeah, it's true. Okay. Thanks so much, Brian. Thanks, Edward.
Yeah, Steve, let me also add another comment to it. So if you can go back to the top level on your folder.
I continue sharing.
Yeah, continue to share. I think you made mention of the phenology, whereby you'll be able to also upload your shape file. So if you can go back, there's now a new folder called use cases. If you can open that folder. Yeah, and do that. We have the Lake Baringo. Yeah, if you can open it. Yeah, I think the vegetation, the first one. Yeah, vegetation. No, the first one. Yes. So this notebook actually allows you to also import your shape file into it, whereby it will actually do the calculation and everything for that specific area you want to work with. It's a use case that we tried with Lake Baringo and it worked perfectly. So you can also pick this notebook, duplicate it, and just import your area of study into it to give you the results.
So this notebook does a lot, and
for the few months I've not been able to go through these. Anyway, I think there is a lot here. Thanks so much. I think I'll have now to explore again.
Quick note on that notebook is that notebook is designed to look at phenology over multiple years, and we were looking at a single shapefile for an area. And so even though this might be a good place to maybe like copy some code and steal it. You could probably copy some of the functionality into your own notebook. At the very top is where the actual importing of the shapefile goes on. And you can actually give a shapefile to the data cube, and it will load it'll create a bounding box around the shapefile, and then it will load the data for that area. So here the shapefile is this Ruko Conservancy .geojson, and if we scroll down some, and the caveat here is that it looks like you're using a GeoJSON file with multiple polygons, correct? Because you want a polygon for each field.
Yes.
Yeah, and there is, believe it or not, another notebook that deals with multi-polygons. So one of the hard parts I think about the data cube is actually going through the large number of notebooks to see this. So scrolling down a little bit more, or sorry, scrolling up a little bit more, sorry. Anyways, we can talk about this later offline if you would like. You can always feel free to email me or email the help desk, and that will also get to me most likely, and or somebody more knowledgeable than myself if you have any questions.
Okay. Thanks a lot.
Okay. So Steve, you can go through it, and if you have any challenges, just reach out to us through the help desk. So we can work on that.
Okay, thank you a lot.
Okay, thank you very much for the work you've done, which is very great. Okay, so the next presentation will be for Brian to give us the presentation. Okay, Brian, over to you.
Thank you. So in the interest of going through some of the notebooks that are available, one of the ones that I don't think is maybe explained as thoroughly, or maybe you need more of a background in math to kind of understand, is the principal component analysis notebook. And let me start sharing my screen. And if you have any questions, please feel free to interrupt me. I am more than happy to be interrupted and explain anything as necessary. But where we're beginning is in the so there's I guess it might be worth going over the just the structure of the folders here. The beginner's guide is this is a series of notebooks in order. They have numbers, right? And they're designed to, this is the DE Africa training that most people have probably already gotten through, but they're designed to just cover some of the basic functionality of the notebook. And then you're left with these kind of other ones. The frequently used code is full of notebooks that are kind of smaller and shorter, but the idea is that they, the code in them should be more reusable, in that they're going to be illustrating a point that you may be doing a lot as you try to use the sandbox in interface with the data cube. So, for instance, there is a short notebook here about exporting to GeoTIFFs, and a lot of these notebooks are actually illustrating certain functions that are in the script section. So a lot of times you'll see at the top boxes, you'll have these import statements from, for instance, DE Africa data handling or DE Africa plotting. And so this is using load analysis ready data, or load ARD. And this one is also using the RGB function. And this specific one is to use this write cog function, but the place to find this is in the scripts folder, one folder up. So we can go to the scripts, and we can actually, if you have a question about these, that's where all of these live. This data cube util is actually part of a core functionality of the data cube. So it's actually not something that you could access directly through the sandbox. You would have to go look at the data cube documentation online. So hopefully those are some tools to kind of like help you answer your own questions as well as you come across them. But in this frequently used code, one of the advantages of using the sandbox is that we have access to the full cornucopia, like the full library, or the full number of libraries that are available for Python. And Python has a very rich data analysis ecosystem. And there are many libraries that have actually quite convenient functions to do very complex things. And it makes it like so much simpler when you're trying to apply maybe a more complex topic to your analysis, and you can access it with a simple import statement. And I think a good illustration of this is the principal component analysis notebook that's in the frequently used code folder. And one thing I just kind of wanted to take a second to go over is I wanted to take a second to note principal component, like what principal component analysis is. But I also wanted to, like as a higher point out that doing this very complex thing is as simple as importing PCA, principal component analysis, from sklearn, the sklearn library. So let me switch screens for a moment. Let's see. Why is my slideshow not starting? I apologize. Okay, share. Okay, so here we go. So the principal component analysis, this is very, very short. This is I literally only have one slide on the subject, but I wanted a little bit of a visual aid here. So the idea of principal component analysis is to try to figure out the coordinate system for your data points that explains the most variation. And so we can imagine that, let's say we've collected a bunch of data, right? And so we have, for each collection, for each data point, we have all these like variables that we've collected. And we want to figure out perhaps what the most important parts of that data is, right? And principal component analysis is really good at that. So, for instance, one of the classical examples is that you have a class of students, And for each student, you collect some data on each one of them. And, you know, maybe you collect their height, their head size, their, maybe where they were sitting in class, maybe the time they spent in class, you know, like their attendance record, and maybe the time spent studying. And you just have a bunch of data points about it. And you want to understand sort of what explains the variation amongst your students the most, right? The grade, you know, like, and you obviously the grade will be one of these. And some of these may not be so important, right? The student height might not be so important. And then other components of this may also be explained off of previous ones. So when you're trying to account for variance, sometimes two things amongst the things you've collected may be completely unrelated, and they would look like this first picture here, right? That there's a complete scatter, and there's not really any correlation between the two. But like, for instance, so this might be, you know, like grade and height, but perhaps you have two variables. So this would like be grade and height here. Perhaps you had two variables like maybe like head size and height, and they would be highly correlated, or something like that. And it doesn't really make sense to focus on either of these, right? That we have these uncorrelated ones and these highly correlated ones, because the reason it doesn't make sense to focus on this one is that I can describe one of these data points completely in terms of the other one, right? And so the idea here is that you really want to find, you know, what is the main component, right? The principal component that explains the variance in your data set. And this also can be useful because perhaps we have a very high dimensional data set, and we have a very high dimensional data set, and it's like in this bottom picture, imagine if instead this was in 3D, right? The idea is that maybe we could flatten this 3D thing and have only these two coordinates actually explain the complete variation, and we could then graph the data in only two coordinates. And so principal component analysis is really useful for doing things like this. And I thought it would be worth kind of a quick introduction here. So let's go back to the notebook, and let's see if we can actually apply this without actually having to fully understand the system, the math behind it, because the math is kind of hairy. You have to take an eigenvector, you have to make a covariance matrix, you have to take an eigenvector, all that kind of thing. Or you have to find the eigenvectors and rank them. So we import the data from the data cube, and we'll import some Sentinel data here. Hopefully this is familiar, but if you have any questions, or if you would like to interject with anything you might not understand so far, feel free to do so now. Taking a moment to load. Actually, I think I already have this loaded up. Let's see if I think I kept this already loaded up. Yes, I do. I still have this loaded. Okay, so the idea is that there are a couple of one thing that's kind of nice is that for like classification stuff, there's this whole classification tools script that might be interesting to some of y'all. And for instance, this this sklearn flatten and unflatten is designed to help flatten data sets and then unflatten them after you've given them to, for instance, you want to feed a data set through this library, and these are kind of helper, nice handy helper functions that can do that. And so that's what I'm doing here. I'm flattening the data set, and then I can actually take the PCA function directly from the scikit-learn and I can perform a principal component fit in my notebook. Taking it a little while longer. I know we only have a few minutes left, so. Okay, so it created 3 principal components, right? And the original data looks something like this. Let's see if we can view it. So the original data looks like this. We were loading some blue, green, and specifically here we're looking at the shortwave infrared, the near infrared narrow on the Sentinel. There's like a narrow one, and we're looking at the red edge. So this is all kind of in that near IR red area, right? And we can then look at the relative importance of each one of these, and then we can actually take when we do the transform, we can actually take our data and reproject it into this coordinate system, and then we can unflatten it, right? And what we get out when we feed back in these 2 bands, keep in mind these bands are no longer the sphere and the red edge, right? We've actually transformed our data very much like we did in we found the coordinates in which the data varies most, and then we can actually re-show this data with 3 new bands that may be, and each one of those bands is probably a composition, but we can actually see something interesting, which is that the most principal component explains quite a bit of the variance. And so actually visualizing this in RGB, it might be more interested to visualize this maybe just in terms of this one component, right? And this may be, if we delved into it, this could be, for instance, something like chlorophyll or water identification or something like that. But I'm out of time because it is now 6:45. So I'll turn it back over to Edward.
Thank you, Brian, for the presentation. We really appreciate it. Today, the time was 15 minutes, and thank you for finishing on time. Okay, so today we've actually had a discussion from Steve and Brian. At this point, I wanted to find out if there's any question to ask either Steve or Brian, or if there's anything or any project that you are working on that you will be happy to share it with the team here. I think we also have a hello.
Yes, can I ask Brian a question?
Yes, Steve.
Yes, I'm looking at that PCA and I'm wondering, can it be used to gauge the relative importance or the feature importance of the features that are being used in a machine learning task?
Yes, but one of the complications is that the feature may be a combination of, it's most likely going to be some sort of linear transform of your original coordinates. So like if we had in the example in the notebook, right, we're using sphere, near, and like the red edge as
Yes.
our 3 different coordinates, and basically it's created a new coordinates, right? And that first one actually explains most of the variance. So it, maybe in a later session we could look at the histograms of where the different pixels land in the 2 different coordinates things, and that would help you kind of understand like what is important. And it'll tell you what is most important, like where the most variation in your data set is.
Okay, that would be much useful. Thanks, Brian.
For a specific suggestion to you, though, is that linear discriminant analysis may be more applicable if you already have classes of things. And so LDA or linear discriminant analysis may be worth looking into.
Okay, thanks.
Okay, thank you, Brian, for answering Steve's question. Any other comment? I think Mr. Sulemana, please can you greet us? Yes, if you can tell us where you are calling from. You are muted. We can please unmute yourself. Can I hear you? Okay, you can speak now. Just we cannot hear you. Maybe I think maybe that there's a problem with the mic, but don't worry. Mr. Sule, nice to meet you. Yes, it's a pleasure that you have to be part of the community. So every Wednesday we have this live session that we try to talk about things in relation to Earth observation. So welcome to the family. Okay, so thank you, Binance.
Excuse me?
Hello, Majero.
Oh, yes, I have a question to Brian.
Okay.
So for the PCA, after calculating the variance for and finding the important component, assuming there are like two components that affect the data, are you going to combine them or will you calculate them differently?
So that's kind of up to you and what your use case is. What one use case that I think I kind of forgot to touch on in the intro is that if I have that 3D, or maybe I didn't explain it fully, that I can start ignoring potentially some of the other components if they don't explain much of the variance, because I wouldn't lose so much information. So like, imagine that I had a bunch of data that was kind of Gaussian, like distributed as like a Gaussian, right? Like, but it was like kind of like at an angle in the 3D plane, right? It would tell me the two components I would need to transform, or the three components like potentially I could transform into. There may be some noise in this dimension, and then in this dimension or something like that, and then I could drop off the component that has the least variance, and it would allow me to then project it into a 2D plane, and that might be helpful for me for understanding my data. What the components are is also very helpful for understanding what explains the variation in your data. So like if I had all that data on the students and I wanted to understand what provided like the most variation, right? Like I imagine the grades are going to be a large variation, but then I was kind of wanting to understand what the other components in this data set provided for a lot of variation. I could then look at the grade vector, and then maybe the time spent in class vector, and maybe that would rank very highly as something that would explain the variance, if that makes sense.
Oh, yes, it does. And do you always assume that the relationship is linear or chaotic, or it depends with the situation?
Yes. So yes, it does depend on the situation, and sometimes PCA will fail and it won't give you very good results, because if the data has some sort of structure that can't be linearly transformed to explain the variance, it will fail. And I know that's a very like high level kind of wavy thing to say, but imagine that I had data points all in a circle, right? And then I tried to run PCA on this. The problem with that, even if it's like in higher dimensions or something like that, the problem with that is that the most of the variance would be described by like a transformation into like angle theta or something like that, right? But that's not a linear transform. And so PCA will fail because I can't actually figure out theta through the actual math that gets me to the principal component analysis. So things that are a little bit too complex may not work. I'll kind of leave it. I'll leave it as that.
Have you handled the situation where it's chaotic, or
so chaos is fine, noise is fine, and so this is good at finding, for instance, signal and noise. If you have especially we're kind of talking about like Gaussian kind of mixture models and that kind of thing. The Wikipedia page on principal component analysis, like many math topics, is very, very dense, but it also may hold clues to like there are crazy it's a very deep topic, I guess, and this is like just wetting our toes a little bit, but it allows us to access that powerful math. So if it's chaotic, if it has some noise, that's okay.
But if the relationship is nonlinear, it might be a bit challenging.
Yeah, maybe it would not be a good tool to use. Yes.
So have you been in a situation where you needed to handle such data, or?
Yes. The I guess a good, if there was something you could imagine that if you had a time series data, right? That the vector may actually like your data points in space may actually be making something similar to a circle, because they may be going through browning and then greening and then browning and greening throughout the year. And that may be hard to tease out if it may give kind of, the problem is that when it fails, it's not completely clear. I will say that's a big drawback, right? That it will still try to get, it will give you something, right? The process to get to the principal component, it will give you something, but if your data potentially has that that property, right, that may not be the you have to watch out for it. You have to understand the data beforehand before you apply it, I guess is the best warning I could give to anybody, right? Like if you knew it had some sort of nonlinear, so like in DVI, like for example, right, is nonlinear transformation. Anyways, I think hopefully that answered your questions.
Yes, it did. Thank you very much.
Okay, so thank you, everybody. Please, if you have any other question, you can reach out to the help desk. It's helpdesk@digitallightafrica.org. If you're able to reach us there, if you have any question, you can also post it there. And also, next week we'll be upgrading the sandbox. So please, if you have any data on the current sandbox, currently download it. Otherwise, all those information that you have on it, you lose them, except the default one. So please, if you have any customized data that you work on into the sandbox, please download it so that when we upgrade it, it won't have any effect on those. You can have those files back and upload them again. So thank you, everybody, for making it up this week. If anyone has a new presentation that you would like to give next week, kindly reach out to Ken or I on that, then we can book you for next week also. Thank you, everyone, and wherever you are, have a great day and great night. Bye-bye.
Thank you.
Bye.
Thank you.
Thank you.
Bye-bye,
Thank you. Thank you.